So in the previous video, I just explained the concept of building being modeled as a lump capacitance model. But there are some technical requirements and we must fulfill those requirements to start modeling our building as a lump capacitance. So there are two of the requirements. Let's just start with this topic of requirements to model building. I am right now specifically concerned about modeling the building, but these are the general requirements to be fulfilled if we want to model any of our mass, any of our structure as lumped mass. Lumped capacitance. So there are some technical words we must understand: model, building, lump capacitance, and we'll be talking about the requirements to do it. So the first requirement is my mass or the building should have small enough size, and the second requirement is large enough thermal capacity. Thermal conductivity would be a better term, I think. Thermal conductivity. So obviously the conditions are relative. Small enough and large enough doesn't make sense directly when we are doing some calculations or doing mathematics of it. But I'll just give you the background of why these two conditions make us model the building as lump capacitance or any structure as lump capacitance. So if having a small size of our mass or the building, then the temperature can easily change. The heat can easily transfer from one point to other point. If the structure is so large, if it is an Eiffel Tower, changing or transfer of heat from one end of the Eiffel Tower to the top of the Eiffel Tower takes some time. But if the Eiffel Tower is so small, then those heat can transfer very easily. And the second factor of that heat transfer is the thermal conductivity. So if the thermal conductivity is very small, then even if my structure is so small, even if the structure is just this much, but it is an insulator, let's say it is a plastic, then the transfer of that heat from one end of that plastic to another end, even if it is small, will not take very easily because it is an insulator. But on the other side, if I take a copper ball, then the transfer of heat will be very easy because it is having a very large thermal conductivity. So if I should have small enough size and large enough conductivity. Even if we have a very large size, but the thermal conductivity is also very large, then we might be able to model the building as lump capacitance. And on the other side, if my building is very small, very small, very tiny, and my thermal conductivity is not that large enough, then also it might be possible to use lump capacitance model. So formally the condition is here. The condition is given by something called as Biot number. Which is Bi, and then it is defined as HLC by K, and the number should be less than 0.1. If I want to use the building with these characteristics, H, LC and K are the three numbers which we determine. And if the number Biot number comes out to be less than 0.1, then I can use the structure or the mass being modeled as lump capacitance. So what are H, LC and K? These are the three factors which will make it determine. So H is the surface heat transfer coefficient. LC is the characteristics length and K is the thermal conductivity of material, or the overall thermal conductivity of my whole building. So these are the three factors which will determine and make sure this. How are these three interplays happening? So this determines the speed through which the heat transfer can take place from the surface. So if I have a body, let's say we have this is my body, and the H represents the heat transfer which is happening from the surface over here. Sorry about that. So this heat transfer from the surface determined by H, right? The heat transfer inside my body, this is my material, and the heat transfer from this location to this location is determined by K. K is the thermal conductivity of the material, which is used in the Fourier's law. H is the surface heat transfer coefficient, which is the convectivity, which is used in the Newton's law formula. I'm just giving analogy so you do not get confused. And LC is the characteristic length. So if I have a square, my characteristic length is the length of the side. And if it is a rectangle, now it depends. What it depends on, if the heat transfer is happening from these surface areas, then both of the surface areas, then the length becomes this much. This is my LC. If it is happening only from one side, so if my rectangle is such and this is insulated, there is no heat transfer happening from this side, it is only happening from this side, then my LC is this whole length. So basically for the formula for LC is the volume divided by surface area for heat transfer, volume in which heat transfer takes place, divided by the surface area, the total surface area from which the heat transfer is taking place. This is very simple formula, and it works everywhere. So if I use this formula on this side, what happens is, and for sphere also it can be very easy. The LC could be LC by this could be 3LC or LC by 3, but it depends. Very easily the formula would be 4/3 pi r cube, and if the heat transfer is happening from all the surface area, then we know the surface area is this much. Hence my LC will be equal to, the 4 gets cancelled, pi gets cancelled, r square gets cancelled with r cube. So my r by 3. So if this is r, then LC, this will be 3LC. But it's very simple. This is the procedure to calculate the characteristic length. And I hope you understood the concept of lump capacitance and the requirement which is defined by the Biot number. And if you want to have a more detailed understanding of the derivation and everything, then I have a separate heat and mass transfer playlist on my channel, and all the whole chapter, whole module on lump capacitance specifically, which is covered in thermodynamics or heat transfer course, is available there. So you can go and look at there. Thank you.